All right, this will be the last video for this lecture. I did want to mention the second derivative test. So this is another test to classify local extrema. So we're not actually learning anything new. We're learning a second way to do something we already know how to do, and that is classifying local mins and local maxes. So here's the setup. Suppose f is continuous near a certain point, so you just need to be continuous around it on some little interval. If f prime of c is 0, so the derivative exists at c and is 0, and f double prime is positive there, that means you're concave up, then f has a local min at x equals c. If f prime of c is 0 and the second derivative is negative, this means you're concave down, then f has a local max at f equals c. And I wanted to show you a picture of this. Somehow the picture makes this clear. Just draw yourself a local min and a local max. And now think about concavity. You are here. I'm definitely concave up, right? The graph is above my tangent line. And so in this case, what's happening is, look, if you have a horizontal tangent and you're concave up, then that has to be a local min. If you have a horizontal tangent and you are concave down, then it has to be a local max. That's what the second derivative test is really saying. So I thought we'd redo this favorite example of ours. Man, we've gotten a lot of use out of this function. Let me zoom back in, sorry. We've gotten a lot of use out of this function. So the old way with the first derivative test, which by the way, we're going to keep doing. The first derivative test will usually often be your go-to test, but there are times when you want the second derivative test. The old way is you take f prime, you find its zeros, you make a number line, and you label it with the signs, positive minus positive, just a sign diagram, and then you can actually just see you have a local max at -1 and a local min at 3. So there's really, this test works great. It doesn't seem like we need another test, but you haven't seen the problems that we're going to be doing in the future. So how do you do it with the second derivative test? Well, you still find the first derivative. You still want to factor it if you can, figure out where it's 0, and you're going to get, let's move this little guy down. We're going to get that f prime of x equals 0 tells me that what x equals 3 and x equals -1 are solutions. So the idea is you find the second derivative, and then you want to plug these critical points of f prime into the second. These are special critical points. So these are the critical points where f prime is actually 0, not undefined. So look, f double prime of 3 is, just plug 3 in, 18 minus 6 is 12, is positive. So the second derivative test tells me that f has a local, it's kind of backwards to what you expect, a local min at x equals 3. That's the first one. And then secondly, you can see f double prime of -1. That's going to be what, -12. That's negative. So f has a local max at x equals -1. Now, I had said I was going to possibly have a short video. I think we'll just go ahead and finish out this section with one big example where we put all of this together and try and work it out. So here's the example that I want to work out with you. So our goal is to sketch a graph that includes all relevant data. And we'll talk more about curve sketching in a later section, but already we have the tools in place to be able to do this. And so just a couple of things. When you're sketching these, you really want to have your mind fully on and pay attention to whatever details you can note. These details might help you. So for example, before I think about anything with the first derivative test or the second derivative test, I'm just going to approach this from just a very, very basic perspective, and I'm going to realize that, look, f of minus x is minus x over minus x squared plus 1. That's minus x over x squared plus 1, which is minus f of x. So I can see that f is odd, Now, why does that matter for sketching a graph? Well, because I have symmetry. I have symmetry over the origin. So I know now that my graph should be able to be reflected over the origin. That's really useful. So you definitely want to pay attention to any kind of symmetries you might have. And a sip of my coffee, sorry. The other thing that's worth noticing on this problem, just a tiny thing, but if you take the limit as x goes to, actually we'll see plus or minus infinity, it doesn't matter, of f of x. So I'm going to let x get big, either big positive or big negative. And look at what happens. As x gets big, the bottom is going to get bigger faster. Maybe you'd like to see this worked out precisely, so maybe we should actually do, let's just do positive infinity, and I'll claim that the other one is the same. This is the limit as x goes to infinity of x over x squared plus 1. The form is infinity over infinity. So what do? You use L'Hopital, and you get what? 1 over 2x plus 1, and now that limit is just 0. Same argument actually tells you that, I'll say similar because it's not exactly the same, but similarly, let's just say, similarly the limit as x goes to minus infinity of f of x equals 0. So, wow, I didn't even apply any of the new stuff we've learned, and I already know quite a bit about my graph. The graph is going to get closer and closer to the x-axis as x gets large, either large positive or large negative, and I know that there's going to be symmetry across the origin. So now we are ready to dive in and work out the different tests. Let's do it together. I'm going to go ahead and begin by just computing the first and the second derivative. We're just going to get that out of the way. So f prime of x, we're going to have to do the quotient rule. So we'll take the derivative of the top is 1 times the bottom. We're going to subtract the top times the derivative of the bottom, and then we're going to be all over the bottom squared. So this is just 1 minus x squared over 1 plus x squared squared. This factors as 1 minus x, 1 plus x, 1 plus x squared squared. A couple of comments. When we compute the second derivative, I'm going to want to start with the simplified but unfactored form of f prime. Second comment is 1 plus x squared. Why I switched the order here as beyond me, but it's the same as x squared plus 1. But the point is x squared plus 1 is never 0, right? Why is that? Well, if you solve, you'll get x squared equals negative 1, which has no real valued solution. So the denominator is never 0. That's good. I'm going to be able to make a nice number line for f prime. Let's go ahead and compute f double prime. I would actually encourage you to compute it yourself, and you're going to get something rather interesting. I'll actually write out the first line. You're going to get, with the quotient rule, minus 2x times the bottom. I'm working off of this version of the first derivative, by the way. So just applying the quotient rule, 1 plus x squared squared minus 1 minus x squared the top times the derivative of the bottom is 2, 1 plus x squared to the 1 times the derivative of the inside is 2x, and then all over the bottom squared. So that's 1 plus x squared squared, so to the 4th. And I'd like you to pause the video and try and simplify the top. Factor out what you can, combine what you can, and then see what you can do. So in the end, you should be able to work out the second derivative is 2x, x squared minus 3 over 1 plus x squared cubed. That takes a little bit of work, but you need to do that work to be able to make your number lines and sign diagrams and so on and so forth. So now I'm ready for a sign diagram for f prime. I can look at the top and I can see that, hey, f prime is 0 when x is 1 or when x is minus 1. So I'm just going to put minus 1 and 1. I'm going to plug in something really big. I'm going to plug in 10 billion, oops, I want my my highlighter, not my marker. 10 billion squared plus 1 squared is definitely positive. So when I plug in 10 billion, the bottom is positive. I'll make just a little sign chart. Bottom is positive. When I plug 10 billion into this factor, that factor is positive, but 1 minus 10 billion is negative, so I have a negative times a positive over a positive, which makes this guy negative. You can keep doing that, or you can just instantly recognize with multiplicity that the other ones are going to just switch sign. Both 1 and minus 1 have odd multiplicity. So I've got that sign diagram worked out. I'm not going to write it all out right now, but instantly from this sign diagram, I know that f is increasing from minus 1 to 1, and it's decreasing from 1 to infinity and minus infinity to 1. I know it has a local min at -1 and a local max at 1. That's all there if you have eyes to see it. Second sign diagram for f double prime. Let's go over here and make sure that we see the zeros. If you set f double prime of x equal to 0, you're going to get x equals 0 or x equals plus or minus root 3. So I've got negative root 3, 0, and root 3. And again, plug in something big. I'll plug in a billion. That seems big enough. Well, a billion times 2 is positive. Squared minus 3 is positive, positive. So everything is positive. And I'm just going to use multiplicity and instantly fill in the rest. You can plug in points if you need to. Make sure that you can work that out. Either way, it's very important. And now at this point, I know where I'm concave up, and I know where I'm concave down, and I know where the inflection points are. So a lot of these problems, you'll be asked to list out all that information on an exam. I would ask you to list it. So I think I'll do exactly what I would ask you to do. Let's write it out together. So f is increasing on minus 1 to 1. F is decreasing on minus infinity to minus 1 and 1 to infinity. F has a local max. Let's go up here again, positive, negative. Local max at x equals 1. And we can plug in, let's actually go ahead and compute it. So the local max is going to be of f of 1 equals 1/2 at x equals 1. I'm going to have to switch pages here, that's fine. So f has a local min of, the local min is right here, right? So local min of f of minus 1 equals minus 1/2 at x equals -1. And that's everything the first derivative is going to tell me. Now I'm going to go to the second derivative, and I'm going to say, well, okay, from the second derivative, I can see f is concave up on the intervals minus root 3 to 0, and then the interval root 3 to infinity. I can see that f is concave down. I'm just reading off of here, right? Concave up here and here, concave down there and there. So f is concave down on minus infinity to minus root 3, and then also 0 to root 3. And I should also list the inflection points, right? I'm changing sign here, here, and there. So f has inflection points at x equals 0 and x equals plus or minus root 3. Woo, okay, now that's all the information that you could write down on an exam. I'll ask you for some, if not all of this. But the last thing we need to be able to do is to put all this together to make a graph. So let's do that together. Here is our graph. I'm going to make it big, not that big. And I'm going to go ahead and try to capture everything. So don't forget that we figured out that there's symmetry. I'm going to scroll up. There's symmetry. This function is odd. And also, as x shoots out to plus or minus infinity, the function's going to 0. So I'm going to scroll down, and I'm going to put some little guidelines. These are going to be orange flags that may or may not actually be on my graph, but I know that somehow I'm getting closer and closer to 0. I don't know if I'm going to be above the x-axis or below. I'm just going to put an arrow here and an arrow there. Somehow your graph has got to get back to the x-axis as x gets large, and then there's going to be symmetry as well. Let's try and sketch those local extremas. I'm going to make this my 1, and this is going to be my -1. Okay, and 1, we went up to a half. We said, look, there's a local max at 1 comma a half. So I'm going to put that. Let's make the actual color of our graph. I don't know. How about green? Let's do green. So we're going to go right here. That's a local max. So I'm going to go ahead and plot that. And then I had a local min at -1 of minus a half. So I'm going to plot that. By the way, don't forget the y-intercept. That's pretty easy. If you scroll up to your function and you just plug in 0, you get out 0. And that's the x-intercept and the y-intercept in this case. So that's just a point. You can use your old school technique of just plotting points. Don't be afraid to do that if you need to. So I've got these particular points. All right, that's that. Now what's happening, it's worth noting that this function f is only 0 at 0. So I'm going to go ahead and mention a little sign diagram for f. I'll squeeze it in up here. If you make a sign diagram for f itself, it's positive when you're bigger than 0 and negative when you're less than 0. So I'm actually kind of done with this side. I've got to go from this local max and I've got to get down, down, down. Whoops, I slipped. I've got to get local max down, 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 down. Okay? And local min, I've got to stay negative and get closer and closer and closer to 0. I need symmetry here, which I probably just lost, but that's okay. And then I've got to connect through this point. So it's going to look something like that. Now the only other thing that we don't really have at this point is we haven't worked out the other inflection point. So there's an inflection point at 0, but there's also an inflection point at root 3, plus or minus root 3. Root 3 is roughly 1.7, and you can check f of root 3 is roughly 0.43. So over here, a little closer to 2, there's going to be another inflection point. Let's make this root 3, and somehow that's another inflection point. And then over here at minus root 3 is going to be over here, and there's another inflection point there. And here's the deal. Bottom line, these are hand-drawn graphs. You're not going to get them perfect. If you will simply get the local extremas correct, and you will plot the inflection points, the concavity will work itself out. So I can go back and check now. Let's check. I wanted to be concave. Let's go up at my number line. I wanted to be concave up on minus root 3 to 0. Well, are we concave up here? Yes. You can see, actually the way that I've drawn it there wasn't quite right. But we are concave up. We're going to come around and then bend down like that. And now I'm concave up on this side. The graph is above. And then I wanted to also be concave up from root 3 to infinity, which I've got. I'm kind of flattening out there. You can see that. I'm concave down. On this side, the graph is below the tangent line, and so on and so forth. I won't belabor it anymore, but you want to check that your graph works. There's a slight mistake in my graph. I'm supposed to have symmetry. I should be able to flip this across the origin and get the same thing. It's a little bit bunchy. This is a hand graph. I'm not expecting perfection, but we ought to be able to graph it and then put it on Mathematica. I'll make some Mathematica graphs at some point for you guys. But all right, you made it. We made it through the Homework 19 material. Homework 19 will be due on Tuesday of next week. So you'll have Monday to kind of work through the videos, and then Tuesday you can work on the homework, and it's due at midnight Tuesday night.